All right, so I think we got everyone back. So let's start out. So what did you guys think were the shortcomings, or not so much shortcomings, but limitations of what the spec does not cover that you might want? I don't want to jump in, or I'll pick on some names. Caleb. Don't think we can hear you.
I wrote about how it doesn't really address liveliness, which is a property that you might be concerned about.
Yeah, okay, so liveness certainly is a good thing to keep in mind. So liveness, what do you guys think? Is liveness sort of coming out of CompCert spec or not? It's certainly different from, so the standard thing we've been talking about for the most part so far is things like safety properties, and those CompCert does address. So liveness, just to remind you, is these properties that say eventually the system will do something. So in the context of a C compiler, imagine a liveness property is something of the form, I know that my C code should eventually give me the result I want. Will the compiled code give me the result I want, or will the compiled code just sit there forever, never giving me anything? So interestingly enough, we'll go into details later in the lecture. I think actually CompCert gets liveness properties. I don't know if they sort of aim for it directly or not, but I think that the way they formulate their correctness condition, they have infinite loops as a special kind of an outcome. So if you never get anything done, or you never terminate, that's one outcome, versus terminating and returning something is a different outcome. So I think for them, spinning around forever and not producing anything, any result or any trace of actions, I think is going to be a difference of behavior. So I was also initially thinking liveness might be a thing they don't handle, but I think for a string, I think it actually comes out of their definition, interestingly enough. We'll look at the details later, so I don't have the sort of definitions worked out on my screen so far. We'll get there. But that's certainly an interesting thing to sort of keep in the back of your head, like how are they capturing liveness, or whether they are.
This could, yeah, it's very easy to get confused about this. Don't forget, you can't ask for CompCert to tell you whether or not your program terminates, because that's undecidable.
Yeah, that's a good point also. There's a level of meta-ness about this whole compiler. So we'll try to hit on this later, but so far we've been really talking about a particular implementation in the sort of series of lectures we've had in the class so far. We have an implementation, some piece of code, and we're going to reason about how that code runs. And in the context of a compiler in CompCert, the reasoning is sort of one level abstracted away. There isn't any concrete program that we're talking about. So who knows if the program we're talking about will do anything useful, or whether it'll terminate or not. We have to quantify over all programs. There's a sort of one level of abstraction introduced by the compiler. Turns out to work okay in Coq and in the way they encode it, but it's a little bit more abstract than the usual refinement story we've seen so far. Anyone else? What else might not be in CompCert's spec?
Well, things that come immediately to mind are like performance and security. So like, let's say the practicality of this CompCert is just completely nullified if, it does the right thing, but takes, exponential time to finish.
Yeah, so there's actually two kinds of performance. I think you're absolutely right. So one is, does the compiled code run fast enough? So you had a piece of reasonable C code, there's nothing crazy about it, but in principle, the compiler could turn your nice, efficient piece of C code into a hugely inefficient compiled program. And then now you're not so happy, even though the theorem holds. And that's pretty tricky to state things about. There are sort of research papers out there on complexity of code, and you might imagine trying to maybe state this about the complexity of the C code versus the complexity of the assembly. That's a very murky space, and I don't even know if asymptotic complexity is the right valid thing, because what you actually want is how many cycles on a particular CPU is this going to take, and is it going to take 1 cycle or 1,000,000 cycles? That matters a lot, maybe more so than asymptotic complexity, because it's hard to imagine the compiler introducing something exponential into your code when you wrote a linear algorithm, but you could imagine constant overhead being introduced by a compiler at every one of your steps. So the algorithm is still linear, but all of a sudden it's very slow linear. So that's certainly a big deal. And I think this has nothing, the CompCert spec has nothing to say about that. Another thing that sort of maybe falls in this performance category is the CompCert code itself. So how long does CompCert take to run, and whether CompCert will produce a useful outcome for any particular program. So the paper touches on this, and they basically say, well, you shouldn't worry about this so much, and they don't provide it. But this is actually an easier problem, because you can run CompCert. If it fails or doesn't terminate, you can, I don't know, debug it. Whereas if you get some compiled code, you want to make sure that however your users run this compiled code, it'll be okay. So I think, at least for this category, this is sort of rightly maybe like a second order property that you wouldn't worry about, or an nth order property that might be not as big of a deal. Anything else you guys discussed that seemed interesting?
We talked about the fact that the CompCert spec doesn't tell you anything about unsafe programs or unsafe behaviors. So if you have a divide by zero somewhere in your program, it doesn't tell you nothing at all about the compiled version of that entire program, for example.
Yeah, so this is another sort of issue, right? Like you want, you know, I don't even know how to phrase this, but like correctness of the app code. So we have a CompCert giving us a proof that the compiler is good, but almost what we, well, at the end of the day, what we want is that the resulting executable that we run is good. And CompCert takes a particularly compiler-centric approach to reasoning about what should the resulting binary be allowed to do or not. And as we'll get to in a second, there's lots of cases where CompCert and many other compilers will produce binaries that do funny stuff, like corrupt memory. And compilers sort of blame this on the programmer. They say, well, you wrote bad C code to begin with. And you could argue probably both sides of the story. Maybe the compiler should help you avoid memory corruption, even though you wrote bad C code. Or maybe you can blame it on the programmer at the same time. So that's certainly a serious issue in practice. And I think you'll see that realistic compilers that are maybe like not CompCert, but things like GCC and Clang and MSVC, they all go to actually reasonable length in concert with the runtime system to try to help the application developer not produce executables that cause memory corruption or have other kinds of issues. So the compiler in sort of Clang and GCC and MSVC with the runtime really goes out of their way to try to help the resulting binary be sensible or safe for some definition of safe. Whereas I think CompCert is much more conservative on that front, really guaranteeing only situations where your source code was correct. And C is a particularly tricky language to write correctly, which makes this problem interesting. That's a good point, yeah, sort of figuring out whether the app code is correct or not. So the other thing I think Bill mentioned is security. This is a somewhat tricky topic, but we'll get to it in a much later lecture in this class. But as it turns out, keeping data secure, keeping like secrets or passwords or keys private in an application turns out to be a fairly tricky property that's hard to get right. And actually CompCert spec doesn't allow the app developer to conclude that CompCert doesn't leak their passwords or keys out of the compiled binary if the binary is processing some sensitive information. But it's a little bit hard for me to, I think, explain on a single sheet of paper here quite why that is. And there's many things here that have to do with secrecy or also timing channels, side channels of various kinds that are hard to get right. All right, anything else in this category? So I think it's a pretty good list of various things to keep in mind. So let's sort of go through maybe an explanation of CompCert, if you will, or we'll pick and choose various aspects of CompCert that seem interesting. And feel free to, as usual, ask questions anytime. So I wrote up here, sort of the top left of the slide, why we should care about this paper. So compilers are, you know, a bit of a PL-focused sort of area in classically, but one really cool thing about CompCert is that it's a real C compiler, and it is used in practice. And it has this proof of correctness we've been talking about. And this is actually one of the big results. So we had you guys read about Amazon and the Everest project in this class so far, and these are certainly big systems results in the distributed system sense of the word. But CompCert is also a serious systems project, a real compiler. And these guys have been around. Xavier Leroy is the main guy behind CompCert, and he's been working on this project for, I think, over 15 years at this point. And it is no joke. And they've been around for quite a lot longer than I think the Amazon guys or the Everest project have been pushing it. So it's interesting to look at their results. And it's extremely widely used in some problem domains. So I think in embedded and air and space context, where the paper talks about the bugs mattering at the level of assembly and are being extremely thoroughly tested. CompCert is actually a widely used tool. It's also widely used in verification as a building block for many researchers. You might argue whether that's used in practice or not, but it is widely used by some class of users in research as well. And not so much doing research on CompCert proper, but using it as a tool to enable further verification. All right, so one question that might be interesting to talk about is why do we want to verify a compiler? It seems like a maybe slightly weird piece of infrastructure to worry about. So the paper puts forward one argument, which is, I think, compiler bugs. And this is, I think, probably indeed a big reason why you might care about CompCert. And compiler bugs are kind of a weird class of bugs you might have in a system, at least from a perspective of a developer. One thing is they're extremely hard to track down. And the situation you're probably facing if you're looking at a compiler bug is you think you have a pretty correct piece of code, you run it, and something funny is happening. You know, you're thinking this should never happen. What the hell is going on in my program? And you stare at your code for a long time. And after you stare at it and can find a bug, you start to suspect, oh, maybe the compiler is doing something funny. But that's really hard to track down because you got to look at the assembly code generated by the compiler, figure out what that has to do with the original code. And that's a tricky process. And often it turns out you have subtle bugs in your own code. So it's kind of a dangerous thing to try to blame the compiler. Often the compiler is not wrong, but sometimes it is. And it is a very difficult bug to track down in practice. So this is one reason why the CompCert guys think it's worthwhile to avoid this really mysterious class of bugs, if you will. The other thing going on here is that compiler upgrades are maybe another reason why it's important to worry about compiler bugs. So it would be great if it was possible to always run the latest version of the compiler. And you know, it seems like a nice property. You can always get security updates, you know, performance updates, whatever comes to the newest version. But if you have a serious project and correctness matters, you might worry that upgrading a compiler is going to cause a problem. That you've tested a system and you've shipped it and you have lots of users. It used to be good. You upgraded the compiler. Is the new compiler going to introduce some bug in one of their new performance optimizations? So one cool thing about CompCert is that perhaps you don't worry very much about upgrading the compiler because the compiler comes with a spec and things are going to be good if they were good before. With some caveats like, you know, this correctness of app code maybe. But indeed, for the most part, you can safely upgrade CompCert. The other sort of problem with compiler bugs, why it might be a serious issue, is that many of your analyses, so if you are looking for bugs, like what we're going to talk about next week on Tuesday's lecture, if you're looking for bugs in your C source code and you say, well, you know, there's no bugs in my C source code, great, I found them all. Then you'd like to know that this is actually true about the resulting program that is compiled by the compiler. So the paper also talks about this quite a bit. So this is actually covered in reasonable detail in the paper. There's other reasons, though, why maybe verification of a compiler is a useful exercise for some of the other side effects. One is really having a precise spec for the source language, so in their case, for C. So actually, I think a significant benefit of CompCert or learning about this paper is understanding what is precisely the spec for C. And far be it from me from saying, in the rest of this lecture, I'll tell you what the spec for C is. That's an enormous topic. But I think it's interesting to sort of start appreciating some of the subtle details of what makes a language specification and what does correctness mean, precisely speaking, in this context. The other thing is that it's a building block for verification. So we'll actually look at some papers later in this class that are built on top of CompCert. And the cool thing there going on is that they can prove some theorem about their code, namely an operating system in the paper we're going to look at. And using CompCert, they just formally prove that the resulting assembly code implements an operating system correctly at the assembly level. And they don't have to reason about assembly code in their proof. That's kind of a cool property. So that's the motivation, I think, for verifying a compiler. Any questions at this level? Hopefully this is mostly just reviewing what the paper is arguing for. Make sense? Any questions? All right. So the thing I wanted to talk about, sort of interesting tidbit I want to cover next, is this notion of undefined behavior. So you guys saw this probably mentioned in the paper of various degrees. But what the heck is this undefined behavior thing? The paper takes it for granted for the most part, but turns out to be a fairly subtle but important detail of a language spec. So this sort of falls in this second category of what I was arguing for, was the benefit of having a formal spec, is we're going to formalize the language as well. So in order to explain what this undefined behavior thing is, let's start out by trying to understand what is a compiler even trying to do in the first place. So the compiler's job is to take some C code and turn that into a piece of assembly code or machine code that's going to actually run on your particular processor. And the goal for a compiler, of course, is to do this in the most efficient way possible. So just by example, you might have a C statement saying A is B divided by C, semicolon. That's a piece of C code. What do we compile it to? Well, ideally, we'd like the compiler to do a very efficient job at this, and basically we want to emit a single machine level opcode, like divide some register R2 by the register R3, assuming that R2 and R3 have the values B and C in them, and that's the end of the compilation, ideally. And we'd like this to be the case for any machine architecture that you might compile to. So you might compile the C code on x86, you might compile it on ARM, MIPS, RPC, RISC-V, and all these CPU architectures. And for all of them, it would be great if you could emit the single divide opcode, whatever that divide opcode is on a particular architecture. And the reason this already turns out to be difficult is because the divide opcode sort of agrees in the common case, but there's all these corner cases like divide by 0 that different architectures might actually do differently. So just as an example, this divide opcode on ARM, on some versions of ARM v7, I think, that actually returns 0. So what we're going to do is sort of consider, what if C is 0? So on ARM, if we were to divide by 0, in R3 perhaps, we're going to get a 0 value back. Well, okay, so maybe that's what our C specification should say is the value of dividing by 0. But then other processors actually return not 0, but actually the maximum value of an integer, just as a way of indicating this error condition. Other processors might actually raise a trap, so you might get an exception or a signal in your process. So this is, for example, on x86. For the most part, you get a trap if you divide by 0. So the question from a language designer's perspective is, how do we write a spec that allows the compiler to do the efficient thing of emitting a single divide opcode, but still somehow handle all these different cases correctly. So the spec can't require it to be 0 or maxent, can't require it to be a trap, because requiring any one concrete thing would cause the compiler to emit more instructions that are slower to run on other CPUs. Does that make sense as the problem statement? Questions there? All right, so the undefined behavior trick is basically to say, well, at the hardware level, something happens. What we're going to say is that the meaning of this statement in the C language is undefined behavior if you're dividing by 0, if C is 0 in our example. And what undefined behavior means in the C language is that anything can happen if you trigger undefined behavior. So if you divide by 0 in this example, all of these are legitimate. Returning 0, well, that's an instance of anything can happen. Returning maxent, having a trap, your program crashes, anything, that's all fine. That's all sort of a subset of undefined behavior. And you can sort of think of it as a specification trick, if you will, for allowing the compiler quite a bit of flexibility in what it's going to do with the code. So just to sort of give more examples of this undefined behavior in the C language, there's lots of things that turn out to be undefined behavior. So for example, if you dereference a null pointer, then this is actually undefined behavior. You shouldn't dereference null pointers. Now, often what happens is your computer crashes, but a possibility is maybe you'll get some memory corruption, or maybe you'll have nothing on some architectures where the null address is actually just a legal address like anything else. It's just not used in C programs then. Another example of undefined behavior in C that's probably not surprising to you guys is out of bounds memory accesses. So if you go to, if you have a pointer pointing past the end of a buffer and you write to it, then you can corrupt your memory and arbitrarily bad things could happen. So you've probably seen buffer overrun attacks or buffer overflows where someone can take advantage of this undefined behavior and cause a program to run arbitrary code. Another thing that's surprisingly undefined in C is actually out of bounds pointers. So it's actually not just illegal in C to access a memory pointer that's out of bounds, but even computing a pointer that goes out of bounds is actually undefined in the C language spec. And the reason for this actually has to do with various pointer representations. So on some architectures like x86 and most architectures these days, a pointer is just a 32 or 64-bit value that describes a memory address. But at the time C was developed a number of decades ago, there are many other architectures that have pointers that look like a segment, meaning that at the hardware level, there's a length field that is associated with the pointer. And pointers are actually maybe a 32-bit pointer value and a 32-bit length or an offset. And in that case, computing an out-of-bounds pointer might cause some kind of an error in hardware because you ran out of the array or struct size. Making out-of-bound pointers undefined behavior allowed C compilers back in the day to have efficient representation of that code as well. And finally, there's other sort of interesting things like signed integer overflow that turn out to be undefined behavior, again, because of different representations. So some hardware might have, ones complement representation of signed arithmetic. Other hardware might have twos complement or other representations. And UB is the trick to allow the compiler to do the right thing for all of them. Make sense? Questions about undefined behavior here? Maybe the last thing I want to say about undefined behavior is that it's not just some historical C artifact, which is maybe one impression you might have from this list is that, who the heck has a segmented hardware architecture these days, or everyone just does, a very specific signed integer representation. Things have standardized since the 70s or 80s. But it turns out even modern languages like Go actually have undefined behavior. It's much more restricted in the sense that you don't have as big of a laundry list as in C of various undefined behaviors. But it turns out to be an important thing even in a modern system. So in Go, maybe the most important thing, kind of undefined behavior to know about is slice operations. So if you haven't programmed in Go, Go is this language that has mostly a safe memory interface. So the way this works is that you might have variables X or Y, which are slices. And what a slice is actually several values stored together. So one of them is a pointer to some kind of a array in memory. And the other is a length field that says how big of a chunk of memory do you have at that pointer. So it almost seems like, well, it is a very nice length checked interface to memory. So there's no way, if you just have a single slice in Go, to go out of bounds. The compiler will make sure that it checks your length field for you. There's another part of this slice called the capacity that we're not going to worry about for the purposes of this example. But for instance, if in Go you say, A equals X of 5, then what's going to happen is that the compiler is actually going to check, if 5 is greater or equal to X dot length, then you get some kind of an error. I'm writing pseudocode for the code that the compiler might emit for this piece of Go code. And otherwise, it'll actually say, A is X dot, actual pointer of 5. So it does this length check for you. Now the problem comes in actually with undefined behavior from concurrency. So in Go, you might have multiple slices. So here's another slice, Y. It's got another pointer to some other piece of memory. And it's got its own length field. So maybe this length field is 2, and maybe the length field in our X was 5. So this is one thread running this code over here. And let's talk about a different thread in the same process that does something like, X gets Y. So you just set the slice X to be whatever slice Y is pointing to. Now, what the code for this is actually, it just copies the field. So first it does, X pointer gets Y pointer, and then it does X len is Y len, and same for the capacity. Now, there's actually undefined behavior that occurs, or at the spec level, the language spec says that it's undefined behavior if you have one thread modifying a slice variable like X over here, and another thread using or accessing it. And the reason this is undefined behavior is because in reality, at the machine code level, like what we see here, this machine code that runs concurrently with this machine code on the right, you could have now a problem because this check that checks the length is not atomic with the pointer access that follows it. So if you do the check first, and then this code sort of sneaks in here, then you check that 5 was in bounds. So maybe actually, let me say, this length maybe was 15, just for our example purposes. So then we do X of 5. 5 is not out of bounds if the length originally was 15. But then, before we go to actually access the memory, this code from the right thread happens, and we dereference the wrong value of the pointer. Now we're out of bounds, and we might crash the program as a result. Go deals with this by making this undefined behavior. So this undefined behavior thing is not just a C artifact, it's a real thing in even modern languages. All right, so this is maybe a bit of a long aside on undefined behavior. Any questions on this before we jump back to CompCert and how it uses undefined behavior? All right, so in CompCert's worldview, this undefined behavior is part of how CompCert talks about program behavior in general. So in CompCert, the way they reason about a piece of code and what it's going to do is in terms of this notation where they say P has a behavior B. And this behavior B basically has one of 3 kinds. So one kind is that the program terminated is an outcome. You ran a program, it exited, gave you some value, and that's the end of the story for this program. There's another outcome called diverges, that basically says the program keeps running forever. It will never exit, or keeps producing stuff and never exiting. And it's not a decidable property because of the halting problem. You can't, the compiler can't decide for you whether something terminates or whether something diverges. But logically, you can talk about a certain program having a behavior of divergence, and then you can prove that if the C source code diverges, for example, then so will the compiled code. And the final outcome is this UB, and the paper calls it wrong. And this is where the sort of third outcome, saying that we triggered some undefined behavior at either the source language level or the machine code level. In CompCert's case, the machine code level, there is no undefined behavior, I believe, because a machine will do something very concrete for any particular input. So undefined behavior is just a trick for specifying out this portable language like C that has to go to multiple architectures. And on any particular chip, things are actually pretty well defined. There's no sort of question like, maybe we'll return 0, maybe we'll cause a trap. Particular architectures have a well-defined spec. And then in addition to one of these three kinds of behaviors, every behavior also comes with a trace of events effectively. And this trace of events is how the program interacts with the outside world. So in the Butler's terminology that he's presented, these are the observable events from the execution of this program. And in CompCert's case, what this trace looks like is that it's a list of external functions like system calls or libraries that are not part of the program. And the trace records the function, the arguments that you give it, and the return value. And it's basically a list of such things that is part of the behavior of the program. So that's how we talk about what a program does. And you can talk about programs having this behavior either at the source code level, so a piece of C code having a behavior, or the resulting assembly code having a certain behavior. And this behavior turns out to be a useful way for us to talk about the correctness of a piece of a compiler and what it means. And just to remind you guys, so our job is to reason about a piece of source code S and machine code C. And we're going to have a compiler that goes from some source code S to this resulting machine code. And we want to state what is true about these guys if the compiler is correct. So the first thing the paper proposes is just basically saying they all have the same behavior. So for any behavior, if the source code has that behavior, then must be the case that the compiled code has the same behavior, and vice versa. You just have the same set of behaviors. So this is definition 1 from the paper, just for reference. So why is this too strict? Anyone want to jump in? So one way we can get a handle on this is through these examples I've sketched out on the right side of the board here. So here's one example over here. We have two functions, foo and bar, and they return some value, but they also print a message before returning. The question is, what will this print statement do if we run it? Any guesses what we should expect the resulting output to be? Well, here's one possibility, sort of a very literal interpretation. Well, what this print statement is going to do is going to call foo, and it'll print foo. All right, so we'll get that. Then we'll call bar and get the bar. And then we'll actually get the values from them, 1 and 2, and print those, 1 and 2. That's one possible outcome. Turns out that in the C language spec, the language spec doesn't actually dictate how the order of evaluation happens. So I think this is the comment Alex just posted in the chat. Indeed, the C language spec says, well, you could also get bar foo 1, 2. So these are both different behaviors. That's like one behavior, and here's another behavior, B2. And it's true that here, the source code could have this behavior, and the source code could have that behavior. But the resulting compiled program is unlikely to have both behaviors, because when the compiler goes to compile this piece of code, it's going to pick some order. It's going to run foo first, then bar, then do the printf. So the resulting C code probably just has behavior 1, or maybe C has behavior 2, but not both. It's very unlikely to have both, because what it would mean to have both behaviors is that the compiled program, I don't know, generates a random number and then decides which order to run these in. That's ridiculous. The reason why the C spec left it undefined was not to force some random number to generate at runtime. The non-determinism in the spec was to make the compiler's job easier, to allow the compiler to do anything within bounds. So this spec is basically too strict. It's going to be precluded by situations like this. All right. So another example of this is sort of uninitialized values, just to show this example too. So, printing I equals 5 here is legit because I was uninitialized. C says you can have any value, 5 or 6 or anything else. And again, at runtime, you're probably going to get some concrete value out. So this exact correspondence is sort of too much of a requirement. All right, so here's another example spec that they talk about, which is this formula 2 from the paper, which says that if the program is safe, meaning that it never triggers undefined behavior, so we don't divide by 0 or go out of bounds, then sort of for all behaviors B, if the source code has a certain behavior, then it must be the case that, if the compiled code has a behavior, then the source code must have had the same behavior. Does this make sense as a statement? So this is, I think, what the CompCert paper calls backward simulation. And it's backwards because you're going backwards from the compiled code C back to the source code S. We have a note that you hopefully have read about why this is different from the terminology we've been using elsewhere. So this spec is actually pretty good. I think this spec is actually intuitively the right spec. It matches what Butler has been arguing as a specification of trace inclusion. So you can read this spec as the set of traces, behaviors produced by the compiled code are a subset of the behaviors allowed by the source code program. So another way to think of such a spec is you ran the executable C, and the executable C did something, B. Now, as long as you had a promise that you never had any bugs in your code, like writing out of bounds or dividing by 0, then the statement says, whatever the C program did, you can blame the source code for it, so to say. So whatever you saw the compiled program do, well, it was possible for this to happen in your source code as well. So if you saw something undesirable from the executable binary, well, it was also an undesirable thing in your own source code. So it's not the compiler's problem. So in this sort of blame view of the world, the spec says that the compiler is not to blame for anything that might have happened to your executable C over here. That make sense? So does this actually work out for our examples over here? So I think indeed it does. So for this first example, if our compiled code has this behavior, that's okay. It was an allowed behavior of the source. If this was the case, then yep, that's also okay. That's another allowed behavior. Same thing for this example, example 2, because whatever we print out from the resulting assembly code or executable, well, it's allowed by the spec because the spec allows us to print any integer value here. Here's another example where we actually have undefined behavior, maybe. So we have 0, and then we compute j as 5 divided by I. That's 5 divided by 0. And then we print hello world. So one possible execution of this is some kind of a crash, or because we divide by 0, so the program gets a signal. So I think that's one possible behavior. Another possible behavior might be that we print hello world. And actually, maybe I should be a little bit more precise. These are not necessarily behaviors of the source code. These are behaviors of the compiled code. So we compile this program, we could get a crash because it really divided by 0. We could also get hello world, And this is an example the paper talks about. The reason we might get hello world is because the compiler does some optimizations that says, oh, well, you didn't use J, so I'll effectively cross out this line, and then you didn't need I can cross out that line too. Your program is just printf hello world. So both these are behaviors of the potentially resulting compiled code, and this is justified because S actually goes wrong. So S has the wrong behavior, and then this specification 2 applies in a trivial way because this S actually is not safe. So it's okay to crash, it's okay to print hello world. Would have been also okay to print not hello world or whatever else. But at least spec 2 holds for this, all 3 of our examples. Does that make sense? Questions about this? So one reason why this turns out to be a difficult thing to reason about directly is because you have to consider, if you're doing a proof of this statement 2, you have to consider all possible values of C. And in particular, what this looks like in a compiler is C is some function like compile applied to the source code S. And it is kind of a complicated thing to consider, well, what are all the possible outputs of F? Well, you have to consider what are all the assembly instructions the compiler could ever produce. That's a messy thing to be trying to argue about in a proof. Wouldn't it be nice if instead we could basically just talk about, well, what are the possible source code statements we could have in S? And then we could talk about, well, for every source code level statement, how do we compile it? And then we'll argue that we compile it correctly. So that would be a much nicer proof. And this is actually what they get at with their definition 3. And this thing basically says that instead of having to reason about all possible executions of the binary, instead we go the other way, which is kind of weird. So for any behavior that's not wrong, then if the C source code has a certain behavior, then we prove that the resulting binary has that behavior as well. This is what they call forward simulation. And the reason it's forward is for this reason of F. Basically, C over here is F of S. The F is the compile function. And as a result, they can argue forward with this function F. So they consider all possible C programs S over here. And then they say, well, let's look at the structure of S. Could be an if statement, could be an assignment, could be, I don't know, there's like 20 different things that a program could consist of. And then for each one, they argue that F will correctly compile that C source code, and the resulting assembly code looks good. So that's the sense in which this is a forward simulation for them. And the reason they really like it is because it makes for a nice proof in Galena or in Coq, because you sort of can work out how the compiler applies to all C constructs. But the problem is that it's actually not quite the property we want, right? Like we can't use this specification number 3 to argue about our binary doing the right thing. So this basically says that might not even be true about these programs, right? So for example, coming back to example 1 over here, this specification, the forward simulation specification, doesn't apply to example 1 because this program has 2 different behaviors at the S level, but only one behavior is going to be chosen by the compiler for the C assembly code level. So this theorem just doesn't hold. There's 2 possible B's over here, only one B could be here. So the way they get around this is they basically show that this is a sensible theorem to apply if your source language is deterministic and the assembly language, the target language, is also deterministic. And then they prove a lemma that basically says you can go from this definition at the bottom to the definition in the middle, which we were arguing is actually a good definition to have. So it's basically a special case of certain languages where you can prove this statement 3 over here and then lift it to prove a statement 2 about the same compilation process. Hopefully it made some sense. Any questions about that?
But you just said that C is not one of those languages.
Yes, so this is exactly the sort of funny thing the paper doesn't quite address. So let me talk about this whole problem of determinism for them. So how they get around this is, you're exactly right. So they start out with the C language, and this thing is non-deterministic for all the examples I showed you guys. Then they have a number of layers that you probably see in the paper. So they compile from C to this thing called C Lite, which is a simple version of C that they define. Then they have another thing called C minor and many other languages in the stack, until they finally get down to machine code at the very bottom. And machine code, at least in their worldview, is deterministic, and that seems like a reasonable assumption. And what they do is they actually make almost all of their intermediate languages deterministic. So everything from machine code up, all the way, I believe, to C Lite are all deterministic. So what they do is they make these proofs go through using their forward simulation, and all these guys, these are all forward. And there's only one proof at the very top that has to be done using backward simulation. And this top proof is indeed a slightly tricky argument, and they manually prove this, manually in the sense that without the nice proof structure that forward simulation enables. And then, after doing this messy proof about backward simulation here, then they take all these proofs about forward simulation, they convert them into proofs about backward simulation, and this conversion is relatively easy. They just prove a general purpose lemma that says, if you have forward simulation and your languages are deterministic, then you can get a backward simulation proof of the same statement. So there is basically no proof effort for converting these to backward simulation. And then they compose all these proofs together. So it's probably not too surprising that you have a bunch of languages, they all sort of simulate each other. Then they combine all these layers into a single backward simulation proof that says any execution of the machine code is going to be a behavior that can be exhibited by the C source code at the very top level. So this is their story for how to deal with non-determinism. It is there, but very much like Butler argued for prophecy variables, this messy aspect of the proof, they just push out of the way at the very top level. They deal with all the non-determinism that's there, make everything deterministic. They sort of suffer for this one proof at the top, and everything else is nice and deterministic. So this is generally a good proof strategy in all kinds of cases. Try to simplify away your execution model or this theorem statement that you need so that your proof can be as simple as possible, and then move the complexity into one place. Sometimes a good idea. That makes sense? Other questions about this determinism and how they deal with it in their proof structure? All right. So one sort of thing that the paper doesn't really talk about is how the CompCert model deals with external inputs. So one sort of puzzle you might be thinking about is, I got a piece of code, you run it, it's going to produce different values depending on what the inputs were. What does that mean for it to be deterministic? Or what does it mean for a program to have a certain behavior when the behavior depends on the external world? So for instance, you might have a program, if the user types in 0, then you're going to divide by 0. If the user types in 5, you divide by 5. So what does it mean for a program to have a certain behavior? So I think the way CompCert deals with this is they sort of, I don't know if they literally formalize this in their CoC development, but I think the mindset that they have is that they have kind of an external world in mind, which is this opaque thing that provides inputs. And the external world is going to provide some inputs to your program no matter what. And as a result, you can talk about your program running with respect to a certain external world. And the nice thing is this external world, it's the same for both your source code and the compiled assembly code as well. So you can talk about a piece of C code running in this external world, providing inputs, and you can talk about the resulting binary running in this external world. And you can sort of think of the CompCert theorem as being, you know, for all world then, you know, whatever, CompCert is correct. You know, produces correct code, and this English prose statement is sort of shorthand for one of these definitions of CompCert's correctness from the paper. But the important point is that this whole thing is parameterized by the world, which in their sort of meta theory, I think, stands for all the inputs being provided. So you sort of imagine that there's this for all world quantifier on the outside of all their theorem statements. And this allows them to talk about a program having a particular behavior because they sort of implicitly fixed the inputs that it was going to get up front. Maybe that demystifies a little bit what these CompCert theorems mean. Questions about this so far? All right, so I want to talk about also, what does this proof of correctness look like, or what does it mean to prove the compiler correct? That's another interesting aspect of this paper that is worth sort of picking up out of this reading. So one way to think of it is, let's talk about memory models. So that's maybe an interesting aspect of what it means for a compiler to be correct. So a memory model, for this, at least purposes of a simple discussion, is going to consist of two things. We're going to describe how is a pointer represented and what's in memory. So on the right side, I'm going to draw the actual machine. So I don't know, x86 or something. And what's actually in memory is just an array of memory locations. And there's probably many of them, might not be fully populated if you haven't mapped some pages, but it's mostly a flat array. And what a pointer is just a value, like a 64-bit address. And a pointer just points to some memory location over here. You know, some X over here. Here's another pointer, also a fixed memory location goes here. That's what it refers to. At the C program level, we probably want a slightly different model. So this is a real model of the machine, but it has a lot of complications. So one pointer to one object might accidentally run into a different pointer of a different object. We've got to prove that different allocations don't overlap with one another, so they don't corrupt each other. It's kind of a complicated thing to keep in mind. So what CompCert does is that actually it has a simpler, or different at least, memory model for the C language. And it's kind of a weird model if you haven't looked at memory models before. Instead of having a flat address space like you have in reality, what happens is you sort of think of every object that you allocate in C as being a separate thing. They're not laid out in any contiguous space. They just float out in space, sort of independent of one another. They're just different allocations. Like here's an object with 3 memory locations, like 3 words of memory or 3 bytes. Here's a thing with 4 bytes of memory. Here's a thing with 3 bytes of memory again. And they're not laid out in any order. It's not like one comes first and the other. They're just separate. You just have a bag of these objects. That's your contents of memory. And then a pointer is now a different thing. It's actually a name of which object you're referring to and an offset. So you might have a pointer that says, well, I want to point to this object and offset 2. That would refer to this location. Here's another pointer. It's object, again, an offset in that object. It might point down to this guy and offset 0. That's this element. And just to give a final example, you might have another pointer pointing at the same object, but offset 3. That's this guy. So that's a way of modeling memory for the C language itself. And the reason this turns out to be a fruitful memory model for CompCert is because this actually has some nice properties for reasoning about it, namely that different objects are just always separate. If you do pointer arithmetic, you never end up in a different object. If you overrun this object, you can't ever end up with a pointer that points here. And similarly, if you overrun this guy, you can never corrupt this object or this other guy. So the model captures some kind of nice properties about object independence that your real memory model doesn't have. And the other sort of clever thing here is that all the things that you might do in C that could invalidate this model, like going from one object to another by incrementing a pointer, those are all undefined behaviors in the language spec. So language spec sort of makes it okay to use this model on the left of the slide as a representation of the pointers and memory in the C language, and you can get away with ignoring the cases when the program goes outside of this model. Does that make sense? And then any program that sort of does go outside the model, of course, isn't going to behave nicely. So if you have some corrupt pointer over here, like this guy, that refers to this object, but the offset is 9, well, that's a really weird pointer because 9 is much bigger here. If you compile it, then you could easily end up with a pointer that is a real 64-bit quantity over here, and this 9 causes the compiled code to run into a different object and corrupt a different object rather than this guy that it was pointing to. But CompCert is going to say, well, I don't care because the original program had undefined behavior. You were out of bounds. 9 is too big. So I don't have to prove anything about the resulting assembly code. That's sort of the undefined behavior trick and how it allows CompCert to simplify the memory model for the purpose of reasoning about the C code and about the compilation process. This is a very sort of intuitive sketch. Hopefully it gives you some flavor of what's going on in the CompCert proof, but not a full story by far. Any questions about this memory modeling and how it interacts with undefined behavior in CompCert? All right, so maybe the last thing I wanted to talk about is sort of this proof structure for the compiler and what that looks like. So one thing that you probably saw clearly in the paper is there's a lot of layers, and each layer in this CompCert proof has very precise formal semantics for what it means for a program in that layer to execute. And what a layer is, it's really a description of sort of an execution platform. A platform might be x86 or ARM or some hardware at the bottom, or this execution platform or environment might be the C language. So you can talk about a C program running or the assembly code running or lots of things in the middle running. And these layers are useful for CompCert because it allows you to slowly transform the program from the C level at the top to increasingly lower levels until you hit the machine level at the bottom. And at every step, you argue in Coq that you've preserved the correctness of this program at any given layer. And because you've correctly chained all these layers together, you can then argue that you took an arbitrary program that's in the C language, and you now have a program at the x86 machine code level, and it has the same exact behavior. These layers are a pretty useful proof technique, and you see this showing up a lot as we'll read various papers. CompCert is certainly, as far as compilers go, it's a little bit extreme in terms of how many languages it has. If you look at something like GCC or LLVM, those things have maybe 1 or 2 intermediate representations. CompCert in this paper has 8. I think the version of CompCert that's out there these days has quite a bit more languages and layers, or 8 languages and I think 13 layers. Some of them share languages in CompCert in this paper. But yeah, that ends up being a bit more different languages than a typical compiler has. But the way to think of it is that for CompCert, the benefit of defining an explicit language layer means that the proof might be actually quite a bit simpler. And for them, then it's worthwhile. Whereas in something like LLVM, you're not doing formal proofs about these LLVM transformations, and as a result, you wouldn't really get as much out of defining lots of intermediate languages like what CompCert is doing. And then the compiler itself is structured in terms of many passes that transform a piece of code from C to a program in C Lite and so on. And we saw that in the previous slides where we were talking about determinism. But this sort of structure of a compiler in a bunch of passes, that's actually pretty standard. So pretty much every compiler out there these days, GCC, LLVM, etc., operates as a bunch of different passes on the code that transform the code progressively towards machine code. That's actually pretty similar, and modern compilers have many more passes than CompCert does, but they typically are passes that transform from the same intermediate representation back to that same intermediate representation, like LVM IR, as opposed to being very different languages in CompCert. And the structure of the proof that the paper gives towards the end is really a simulation argument similar to what Butler has been showing in his lectures, with one sort of main difference. So here's the similarity, which is that we're going to argue about, maybe this is the C code, and maybe this is going to be C Lite code or some other layer. And what we're going to talk about, execution here is going to go down. So here we are executing with some trace T. And what we're going to argue is that if we have a step being taken at the C language level, then at the next level down, we are also going to have the same execution step producing the same trace T. And the main thing to keep in mind is there's going to be some kind of a relation here. This is the abstraction relation, very similar to what we were talking about in last lecture. And the proof basically says if you start out with two states, S1 and S1 prime, satisfying the abstraction relation, and you run on one side, produce some trace T, then you can run on the other side, produce the same trace T, and end up in a state that again satisfies the abstraction relation. So this is that commutative diagram that Butler showed in his lecture on refinement. And the only sort of the main subtle thing going on here is, of course, as usual, this theorem says that for all states S1, and the subtle thing is that actually the code that we're running is actually inside of the state here. So this is the meta-levelness of the compiler. Typically, the code is the transition relation that defines how your state evolves because you're running the code. Whereas here, in a compiler, we want to talk about the executions of all different pieces of C code. So the code is actually part of the state that you're running, and the code prime, the slightly more compiled code, is in this other state S1 prime. And we have to talk about now this transition function executing arbitrary code. And this abstraction relation has to relate not just the classical state you might think of as memory, but also the abstraction relation has to define how the code at this C language on the left relates to the slightly more compiled code prime in the language on the right. So this is the one sort of special thing. Of course, from first principles, this is not special. This is just an instance of the simulation diagram. But the way to think about this is a little bit different because the interesting transition relation, if you will, is controlled by the code, and that's part of the state itself.
And we can tell that it's different because you've rotated it 90 degrees.
Oh, there's this other thing. Yeah, so CompCert, coming from a different community, as you've seen, they have different axes, I guess. Yeah, they flip it 90 degrees. They also use different terminology. So what they call backward simulation is what Butler calls forward simulation. But ignoring some superficial difference, yeah, it's a similar story.
I only said that because you might get very confused if you don't realize that the diagram.
Yeah, apologies on behalf of, I don't know, the two communities conflating here. But yeah, so the induction step, if you will, is going to go down the slide in this CompCert style of a diagram. And the correspondence is really across the abstraction relation. All right, so hopefully it gave you some sense of what CompCert is about and some interesting tidbits to take away from it. So this proof structure of layers, that's a convenient trick you'll probably see in various other systems as well. This use of undefined behavior, that's particularly prevalent in C, but shows up in other languages as well, and that's important to keep in mind when reasoning about things. And sort of this question of how to model the memory. Also, it's a real issue to try to understand precisely what is the memory model of the language you're using if you want to really understand what a piece of code is going to do. All right, any other questions about CompCert, any related topics? All right then, so that's it for this lecture then. Feel free to hang around and ask your question if you feel like you just want to ask sort of a smaller scale question. But otherwise, see you guys on Tuesday. We're going to talk about bug finding tools that are used widely in industry.
Can you go back to the last slide really quick?
Sure. So maybe one thing that I'll mention is that if you want to think about the entire CompCert structure, there are sort of more layers hanging off the side. So in this diagram, in Butler's view of the world, the layers stack vertically, but because this thing is rotated, the layers here would stack here. So there's another, C minor, their next layer is going to be another state, S1 double prime, and so on until you get to some S, I don't know, X over here. That's the machine code. And there's an abstraction relation everywhere along the way that connects the C code, and there's, through the transitive chaining of all the abstraction relations between all the layers, CompCert defines a precise relation between what is true about the C source code that is being compiled and what is true about the machine code that is being produced. And all these simulation proofs prove that at the end of the day, the trace T produced by running the machine code on the very right of the slide is going to be the same trace produced by running the C source code according to the C language stack on the left.
Okay, so basically the passes go towards the right and
Yeah, exactly. Yeah. So the passes, these are sort of these are the passes.
okay.
And some of them might actually use the same language. So there's the C minor, I think, actually shows up maybe in a couple of passes. So actually, what you'll see is actually a simulation relation between two states that both share the same language, C minor, but there's still a non-trivial abstraction relation, meaning that the state is of the same type. It's a C minor state, but the states on the left and right of this abstraction relation between the two C minor states are not equal. The abstraction relation is not just equality, it's some slight transformation.
Okay. All right. Thank you so much.
Sure.